Okay, so let's move on to Chapter 13. It's going to cover thermodynamic property relations. Within this, we're going to do just the fundamental relationships between things that we encounter regularly, the PVT, the CV, CP, du, change in DH, and of course the DS, change in enthalpy. And they're all valid, of course, for pure substances. We're going to talk about the Joule-Thomson coefficient, and then develop a method of evaluating these changes when we're talking about real gases. So it's just a little math, partial derivatives and associated relations. So I have a video talking about the partial derivatives in relation to limits. And so going into that, the state postulate. So the state of a simple compressible substance is completely specified by two independent intensive properties. So we need to have, let's see where it is. There it is. So we need to have two independent intensive properties for compressible substance. And all other properties at that state can be expressed in terms of those two properties. So those two properties are like pillars. So we have Z, and that's in reference to XY. We have F, and that equals f of x, which that function. And then it just kind of goes into the derivative of a function, f of x, with respect to x, represents the rate of change of f with x. So it's over here on a function f of x diagram. And then the derivative of a function at a specified point represents the slope of the function at the point. So that's just giving you some information about some of the basic math that we're going to be doing here. So here's an example that you can walk through. We won't, because we'll actually be doing the problems, but if you do need some extra help, save this slide and go through it. It does give you the solution there, and then the means of analyzing it as well. So here's a schematic for 13.1, so you can see that as well. And you see that slope there along with the equation worked out above with this answer. 1.005 kilojoules over kilograms Kelvin, because we're using the Kelvin scale. And then you can see that plotted with your units specified, right? You always want to specify your units, otherwise the numbers mean nothing. So here we're just talking about partial derivatives. Of course, I do, again, have that video if you need a refresher. So typically it's a little bit covered in Cal, so it should be pretty reminiscent of what you have done. But here's the symbol. It's like a backwards, upside down G situation. It represents the differential changes, just like the symbol D. They do differ in that the symbol D represents the total derivative of the function, and then and it reflects the influence of all of those variables when you're taking the total differential. Whereas this backwards upside down E or upside down G or backwards D, it's or like script D, whatever you want to call it, represents the partial derivative change. So it's just the partial, not the full derivative that we're taking. And this is to obtain a relation for the total differential change in Z when in reference to XY for simultaneous changes in X and Y, because we know that when we're changing on an XY plane, we learned it in the PVT diagram that there's also a Z. So it's actually a three-dimensional. We just typically see it on a 2D surface. And then here are those changes in Z's as well. And this is a fundamental relationship for the total differential of the dependent variable in terms of its partial derivatives with respect to the independent variables. So we're just talking about taking limits and how they're associated with each. and then how we're taking them in Z in reference to X and Y, because we're working on a 3D plane. And here it is. There's the geometric representation of the total derivative dz for a function z x of y, right, in reference to xy. And you see these here. You see the xy plane, and then it's with a z with another arrow there. So here's the partial derivative relations, and that's dz, so remember that's the total. And you have m and n, and the order of differential is immaterial for properties since they are continuous point functions and have the exact differentials. So remember, when we're talking about properties, we're talking about them being continuous or consistent. So they have the exact differentials, and so therefore you can see that the equals here. Okay, and then it does give it to you on a like a reciprocal relation right here, and then a cycle relation or cyclic. So here's this function as well, and you can give it on a, I'm just putting all the way back. Okay, so here's the function. My pen's going kind of crazy. Here's the function that's given over there, and then you can start with step 1, and you plug that in through the z, and then it's given this right here, and then you pull that for x, and then it's just working these formulas. We're going to work them down. But this is good practice if you want some extra practice. Here, using the ideal gas equation of state, verified A, the cyclic relation, and B, the reciprocity relation at a constant P, so a constant pressure. And then the solution, the cyclic and reciprocity relations are to be verified for an ideal gas. So that's what we are working for our solution. And then here's the analysis. So the ideal gas equation of state PV equals RT, or PV equals MRT, involves the 3 variables P, V, and T. And any 2 of these can be taken as independent variables, because remember, these P, V, and T, they're all independent variables. So you can take any of these 2, with the remaining one being the dependent variable. And so then you replace X, Y, and Z in the equation with P, V, and T respectively. So, and then you can use it and express it as a cyclic relation for ideal gas. And here it works through the PV equals RT. You do have the substitution and what that yields down here, right here. So it's pretty simple in the maths starting with these. So these are good to work through. Here's another example. And you'll just go through, take the partial derivatives, and you substitute. And this is just proofing it. So here, we're going to get into the Maxwell relations. So the equations that relate the partial derivatives of properties P, V, and T, and S of a simple compressible system to each other is called the Maxwell relations. So that's how they relate together. They are obtained from the 4 Gibbs equations by exploiting the exactness of the differentials of thermodynamic properties. So here you've got the Helmholtz function and then the Gibbs function here. And we're just talking about how they relate to them using the exactness. And then these are the relations here. We've got these 4 relations, right? Maxwell relations are extremely valuable in thermodynamics because they provide a means of determining the change in entropy, which cannot be measured directly. So we can't measure entropy directly, but we can measure it using relations or other things by simply measuring the changes in the property P, V, and T, because we know that entropy is a measurement of irreversibilities. And so we know that irreversibilities, talking about friction, things like that, drastically changes P, V, and T, or maybe in some ways not super drastic, right? But it definitely impacts P, V, and T. And so when we look at those changes, then we can indirectly measure entropy. And just note, these Maxwell relations are limited to simple and compressible systems. So that's all they're going to work with. And then here they are again. Here's another example. And these I'm just really going through so that you have them in case you just need more work. Sometimes I find that the students, it's just nice to see not only me work them out or have a system work them out, it's just nice to have them just so that you can see them already worked out all on one sheet of paper. Okay. And so then we've got the third relation. Let's see if we go through. Yeah, the last Maxwell relation. So this is the third relation, the Clapeyron equation. And so this is during a phase change process, the pressure in the saturation pressure, which depends on the temperature because, of course, pressure and temperature are dependent on each other, is independent of the specific volume. And that's P sat is equal to F in reference to T sat. Therefore, the partial derivative can be expressed as a total derivative. So this is just a rule talking about the third Maxwell relation. So, and this is going forward with which is the slope of the saturation curve on the PT diagram. So this is now getting into where we have the PV diagram and we have those slopes. That's how we get the saturation curve on those as well. And so then it just gives just information. The slope is independent of specific volume, and then you can treat it as constant. For isothermal liquid vapor phase change processes, the integration yields these two below. So it's just telling you how you get these equations that you'll use, just the background information. And so during this, pressure is also constant, so that's an iso. And here's an equation there. And so then you can substitute that into equation 1321, which is back here, and you get 1322 down here. So again, this is just staring you through how we get the equations that we use. And here it is on a PT diagram. And so you see that slope, that constant is yielded there. And it's just represented in a schematic for you. So this enables us to determine the enthalpy of vaporization at a given temperature by measuring the slope of the saturation curve on a PT diagram. So what that means is that now we can take the diagrams and read them, right? All right. And then it can be simplified for liquid vapor or solid vapor phase changes by utilizing some approximations, of course, because we use approximations in all of our solving. And again, at low pressures, which seems to be low temperatures, low pressures, things like that, we can just equate them as equal. Whoops. Right here. We can treat vapor as an ideal gas here. You see RT over P. And then you can substitute those equations into the Clapeyron equation. And then you can integrate between the two saturation states. And then what you get from here is the Clapeyron-Clausius equation down here. And that can be used to determine the variation of saturation pressure with the temperature. It can also be used in a solid vapor by replacing HFG, and that's the enthalpy of the sublimation of a substance. So here's another example, and it's just talking about extrapolating tabular data with the Clapeyron equation. And it goes through there and it equates out what your equations were and how you would put that information in there. And so then this just goes into, according to the equation, the saturation pressure is 5.561. This is really just giving you so much background information and as to how we get these equations, why we use these equations, how we get these table data, how you're able to read the data tables, and how it was all put together. It's really just going into the properties. So here's the relations. This is nice for du, dh, ds, c sub v. So cv and cp. C sub v, that's here. CV and then CP. Circling back, the state postulate established that the state of a simple compressible system is completely specified by two independent intensive properties. And we should be able to calculate all the properties of a system, talking about internal energy, enthalpy, entropy, at a state once we get to independent intensive properties are available. And you know that because when we use the tables, you only need two independent intensive properties, because then we can just go to the tables and get all of that data. And these data points is how they have used the relations to give you information so that you don't have to go and use all of those formulas to measure it yourself. The calculation of these properties from measurable ones depends on the availability of simple and accurate relations between the two groups. And so just going over what we're doing in this section, because I feel like it's to students, it seems like a little thrown in, a little late. Obviously, I want you to be able to work through them. The chances of you getting hired to produce tables and things like this is slim, right? Because it's done. But you do get to see how developed the general relations for changes in internal energy, enthalpy, and entropy in terms of pressure, specific volume, temperature, and specific heats. And also developed are some general relations regarding specific heats. And then the relations developed will enable you to determine the changes in the properties. So it's just talking about how we get that information. The property values at specified states can be determined only after the selection of the reference state, the choice of which is arbitrary. So it's neither here nor there. So here's information for internal energy changes, and we have that definition here, this formula here. Whoops. There it is. What is going on? It's like it's not, I don't think it's picking it up anymore. Okay. It may have died. I'm not sure. So for internal energy changes, it's going to step out how we get these equations 1325, 1326, and 1327. And then, again, just continuing on all the way through to 1330. And then you've got enthalpy changes, and then continued, and continued. And so it gives you first relations, second relations, and then down here, either relation can be used to determine the entropy change. The proper choice depends on the available data. So of course you're going to use a formula for what you have, and that's what you would pick. But you can use either relation. And here's in regard to specific heats. Okay, so you have these two as well. And some additional information here. And just additional. Okay. So when we're talking about volume expansivity and the isothermal compressibility, which is alpha, you can integrate both of those two or substitute them both in, and then you get this Mayer relation. And you should have been seeing this. So this is just how this is just how we're getting what we have been using. So these are the conclusions from the Mayer relation. The right-hand side of the equation is always greater than or equal to 0, and therefore we can conclude that Cp is always greater than or equal to Cv. The difference between Cp and Cv approaches 0 as the absolute temperature approaches 0, so those two are related. The two specified heats are identical for truly incompressible substances since volume is constant, right? The difference between the two specific heats is very small, it's negligible, and is usually disregarded for substances that are nearly incompressible, such as liquids and solids, and that's because the effects of that are negligible. So here's just, it just shows air. U is they're all temperature dependent. The internal energies of and specific heats of ideal gases and incompressible substances depend on temperature only. This is just a schematic showing that. And then here's another example and another solution and how you would analyze that. And this just shows you that Cp minus Cv equals R if you needed to know how everything went into that. And that's the R is that gas constant of ideal gas. So that's how we would get that. The temperature behavior of a fluid through a throttling, so H equals constant, process is described by the Joule-Thomson coefficient, and that's that coefficient there. And when we start talking about that coefficient, less than or equal to 0, the temperature rises. Equal to 0, the temperature remains constant. And then greater than 0, the temperature decreases. And so that's just shown over here on a TP diagram, where H is this constant line. And the Joule-Thomson coefficient represents the slope of H, which is the constant line, right? Because H is constant. And so this is just showing the constant on there. And then here, the temperature of a fluid may increase, decrease, or remain constant during a throttling process. It depends on quite a lot, the pressure, things like that. And so here, it shows you the T and P and then those constant H lines, and in regard to the differing of the temperatures. So constant enthalpy lines on the substance of a TP diagram. So a throttling process proceeds along a constant enthalpy line. So each one of these lines, it's 4 throttling processes. And it goes from right to left. Therefore, the temperature of a fluid increases during a throttling process and takes place on the right hand of the inversion line. However, the fluid temperature decrease during a throttling process takes place on the left hand of the inversion line. So here's this inversion line, right here, this red, and it's the maximum inversion temperature. So that's, you're plotting this limit. And so the temperature increase is going to be here. Increase. And then this is the decrease. Okay? And so basically what it's saying is that from what you can see here, a cooling effect cannot be achieved using a throttling unless the fluid is below its maximum inversion temperature. All right. And then you can look at developing the general relation of the Joule-Thomson coefficient in terms of specific heats, pressure, specific volume, temperature, things like that. And then for H being constant, we have dH is equal to 0 because it is constant. And so then you would just rearrange the equation, and this is the desired relation. So the Joule-Thomson coefficient can be determined from a knowledge of constant pressure, specific heat, and the PVT behavior of the substance. Here's another example, solution and analysis. And then the temperature of an ideal gas remains constant during a throttling process since H is constant and T constant lines on a TP coincidence, so on that diagram. So now when we're talking about delta H, delta U, and delta S of real gases, so gases at low pressures have an ideal gas behavior, we talked about that, and obey the relation PV equals RT. And they are relatively easy to evaluate because they're temperature dependent only, UH, CV, and CP. At high pressures, the gases deviate considerably from ideal gas behavior. So as it, if it's at really low pressures, we assume that the behavior is ideal gas-like. And then as it deviates from that, then it deviates considerably from the ideal gas behavior. And we talked about this in Chapter 3, remember, about the deviation in PVT and using more complex equations of state. So now using that, extending that analysis to evaluate the changes in enthalpy, internal energy, and entropy of a non-ideal real gases. And that's using du, dH, and ds. So here's real changes, enthalpy changes of real gases, and that's plotted on a TS diagram as well. And it even gives you an actual process path so that you can see how those work between your pressure changes. So for isothermal pressure, the dT is equal to 0. For the first term vanishes. For constant pressure, dP equals 0, and the second term vanishes. And so this is just how you're working through those. And then using a superscript asterisk to denote an ideal gas state. So doing that, you can express the enthalpy change of a real gas during processes 1 to 2. So the difference between H and H asterisk is called the enthalpy departure, and it represents the variation of enthalpy of a gas with pressure at a fixed temperature. The calculation of enthalpy departure requires a knowledge of the PVT behavior of gas. In the absence of such data, you can use the relation PV equals ZR T, where Z is the compressibility factor. And so substituting those, you can get the enthalpy departure factor right here. And then the values ZH are represented in graphical form of PR, reduced pressure and reduced temperature, in the generalized enthalpy departure chart. And then here's some more information that you can use for real gas during a process 1 to 2 from the ideal gas tables. And then internal energy changes of real gases. Here's the definitions there, and the U2 bar less U1 bar, and how those are related as well. Entropy changes of real gases, and here it is plotted as well. And you see that change from 2 to 2 asterisk, 1 to 1 asterisk, A asterisk to B asterisk. And it's just giving you an alternative process path to evaluate the entropy changes of real gas. So again, just more formulas and how we get the formulas that we're using. The values of ZS are presented in graphical form as the function of PR, so reduced pressure, reduced temperature, and generalized entropy departure charge, ZS. Okay, and then here you have an example, and what I like about this one is it does a good job of stating the assumptions up top. And then here, the delta U and delta H and delta S of real gases. And so it just gives you, when you know T and P, and how you can get into those answers as Z. And then we can talk about working in from the Z, including that, getting into boundary work. And then getting into heat transfer, everything that we've been calculating. So it's just talking about a little math. It's a good time to brush up again on partial derivatives, and just knowing the relations and how we use those to get the formulas that we have been working, and how we use this information to get the table information that you've been using, because it just doesn't come from everywhere, or anywhere. But it comes from things, and this is where it comes from.